and this fall I did research in coordination with Dr. Jeremy Balin of the Department of Astronomy and Dr. Ryan Lynch of the Green Bank Observatory. My research is entitled High Time Resolution Radio Frequency Interference and Pulse Detection Using Machine Learning Semantic Segmentation. I realize that's a mouthful, so I cut it down to really fast cell phone, satellite, and alien detector. To start off, I want to give a brief overview of what radio astronomy is. It's essentially like optical astronomy, where you'd go out with a telescope and view the moon, and you'd get an image. However, we're dealing not in the visible spectrum, but in the radio spectrum. And instead of receiving an image, we typically only get one pixel, so just one data value, but really fast and constant. And with that, there are two specific areas of interest in the radio astronomy community right now that are of particular interest to this research, and those are pulsars, as seen in the top left diagram, and FRBs in the top right diagram. Pulsars are essentially like galactic lighthouses that are stars that spin very quickly and regularly emit a radio pulse. And because they do it so regularly, they are some of the most accurate clocks in the world. And by timing how quickly and how fast these pulsar pulses come, we can detect those changes and use it to detect things like gravitational waves. That's what nanograv does. Fast radio bursts, on the other hand, are unknown phenomena that come outside of our galaxy. They're typically called FRBs, and their plot is shown in the upper right, and they have this very distinct curve. Also in the radio astronomy community, there are spectral lines and mapping. That's another area of research, and that's shown in the bottom picture, where you essentially create an image out of the radio astronomy data over a long period of time, and that image shows the galactic plane, probably something like the hydrogen density. And for context for my research, we essentially want to create better hardware and better data for every astronomer. And so I fall under a National Science Foundation grant that was given to the Green Bank Observatory. I specifically am working on the machine learning approach to radio frequency interference, or RFI, excision. Because with better instrumentation and observing over wider bandwidths, so meaning we collect more of the radio frequencies at once, we also get more unwanted data, so this RFI. And so my work is dealing with reducing that data while also hoping to automate the detection of desired astronomy signals like FRBs. So this plot on the bottom shows the difference in how RFI has grown over the past 10 years. The top plot is from 10 years ago, bottom plot is from just a few months ago, and you can see how more of the radio frequency bands are actually saturated with unwanted noise. And so how do we do this? How do we mitigate the RFI? We observe the radio signals in frequency space. So just like on the diagram on the right, it's time on the x-axis and frequency on the y-axis. And the pixel intensity values correlate to the intensity of that specific radio frequency at that time. And so you can see where the higher values in the upper portion indicate that those bands are RFI. So those bright bands are stuff we want to reduce. That's not desired data. And our data set is actually 20 terabytes, so that can be unwieldy to deal with. And once we have these images, we call them spectrograms, we process them through a convolutional neural network to flag the pixels as RFI, desired data, or noise. And we do that using something called UNet, and we train it on hand-labeled spectrograms. So with that, I want to talk about machine learning, which in our case, we essentially just refer to convolutional neural networks, which are layers of matrix calculations that allow for optimization over millions of parameters. And on the right, you can see what an example of optimizing over two variables would look like. But with these millions of parameters and tons of matrix calculations, it's highly parallelizable, so we typically deal with non-traditional computing hardware. So to train our model, we take the input spectrogram, we process it through the model, and compare the model's output to the hand-labeled data. And by comparing these differences, we can tweak weights within the model to improve the performance and decrease the loss or the error. And by doing that thousands of times, hundreds of thousands of times, we hopefully get a model that does what we want it to do, detect the RFI and FRBs. And for inference then, all you have to do is process the spectrogram through the model and take the output. One distinction I do want to draw, though, is between classification and segmentation. Classification would be taking an image and outputting one number, saying RFI, not RFI. Segmentation is doing that on a pixel by pixel basis. And so you get 256 by 256 in outputs, not just one. And that is what we were doing. So here's the diagram showing what our pipeline looks like. You start with the raw data, process it through the model, which gives you the RFI confidence output. And then by setting a threshold, so these numbers are 0 to 1, by setting a threshold, we create a mask. So values of 0 or 1 indicating the presence of RFI at that specific pixel. Then this gives you the mask containing the data that you want to excise. And you can excise it in different ways. Here I'm showing just replacing those values with 0, and that you get better data. You can compare the top left and bottom left pictures. For pulse, it's a similar thing, but all you have to output is just the pulse confidence and let the observer do with that what they will. So the benefits are shown in this graph. This is showing the intensity of different radio frequencies over 3 minutes of data, or about 128 gigabytes of data. You can see where the red is the unmitigated data and the green is the mitigated data. And in the left portion, you can see the red spikes that are RFI. That might be satellite, might be radar, anything, but it's not something we want. And you can see that using this technique, we actually reduce it down to the level of where the baseline should be. However, we don't remove the radio astronomy signal, which is present where that other arrow points to. We want to remove the RFI, but we don't want to remove the astronomy signals that the astronomers are looking for. And this plot shows that we're removing the RFI, but not removing the wanted astronomy signal. So how does this compare against other statistical-based methods for RFI mitigation? Well, first, it's generalizable over time and frequency domains. It excises a lot less data than a status quo statistical-based algorithm called RFI find. It actually excises 16% less data. It allows for the observer individualization with that confidence cutoff. And with advanced hardware that's also included in that NSF grant, real-time implementation is possible. And if astronomers want to detect something else, then we can add an additional mask to detect an additional astronomy signal with minimal computation increase, rather than having to come up with an entirely new statistical formula. So this fall, we've also been working on some other things. Since we haven't had access to a general processing unit, inference over a 20 terabyte data set is unfeasible. So I've been working on refactoring the existing code and working on crowd-based annotation so that I don't have to annotate all 20 terabytes myself. But just last week, we got the new project-specific computer up and running with a dedicated GPU and over 100 terabytes of storage. So we can store the entire project on there and have access to great computing resources. So the next thing that I'm going to work on once I get the computer set up is training it with without labeled data, or training it on just the raw 20 terabyte data set that I don't have to label. And that's using an autoencoder as a pre-trainer for the model. I can get into that more if people are interested. But this January, I will be presenting this research at the American Astronomical Society's winter meeting in Honolulu, Hawaii. And with that, I'd like to thank the following people and open it up for questions.
So how do you annotate those images with such discrete RFI and clean data regions?
Yes, that's actually a good question, because typical annotation platforms only might look at, you want to know the exact pixels that a dog exists in a certain image, but that dog might take up half of the image. And so you just go in with a brush, just like MS Paint or something, and just circle all the parts of the dog, and then just export that. And it's actually pretty easy. But with our data, it's very discrete. So you'll have an RFI pixel surrounded by desired pixels. And so even with the minimum brush size that online annotation tools provided, you actually could not annotate our data with it. So we had to create our own. And existing software tools also anti-alias the data. And so we do not want any blurring of our data whatsoever. So that's why we built our own. And it did mean that I had to go in with a pixel size of 1 over all 65,000 images, or 65,000 pixels for each image. So it's very time intensive.
Can you talk more about the other work being done under the same grant?
Yes. So, so the NSF grant also includes a statistics-based approach, and that's being done by Evan Smith. He's a PhD candidate at West Virginia University, and so he's working on that. And then the advanced hardware also is comprised of many other sub-levels that I didn't include, but it includes a next generation of field programmable gate arrays, 100 gigabit Ethernet ports, and lots of other interesting stuff. So it's not just machine learning RFI excision, it's much more.
I know you talked about getting a new computer to run all this on, but before you got that, did you consider using a computing service like AWS or Azure as a stopgap for your computing needs?
Yes, we did. But it was expensive because AWS charges, depending on what hardware you use, about $10 per hour and about $25 per gigabytes or per terabyte stored per month. And so using AWS, even using a $10,000 GPU, the processing time for just 3 minutes of data was still 8 hours. And we still had to store terabytes of data. So it came out to be about $150 to $200 per 3 minutes of data. And we collected 8.5 hours. So even with that, it's unfeasible with our budget.